Hi, in this module we're going to be talking about noise models that can be included in the GLM. So again, to recap, a standard GLM is written in the following format. We have Y, which is the fMRI data, X, which is the design matrix, beta, which is the regression coefficients, and epsilon, which is the noise. So far in the past couple of modules, we've been talking about model building and how to get the best possible design matrix X. So now what we're going to do is we're going to focus more on the variance-covariance matrix V. So in the last module, we kind of assumed that V was an identity matrix and that we had IID noise. But in practice, in fMRI data analysis, that's typically not true, and we have a certain autocorrelation between adjacent time points. And so we have to take that into consideration. So again, this autocorrelation is typically caused by physiological noise and low-frequency drift, which hasn't been appropriately modeled. And so typically in fMRI, we use either an autoregressive model of process of order P or an ARMA 1-1, an autoregressive moving average model of order 1-1 to model the noise. And so single subject statistics are not going to be valid without an accurate model of the noise. So it's quite important. So let's focus on one particular type of noise model and how it's included in the GLM analysis. So we're focusing here namely on the AR1 model, so autoregressive model of order 1. So serial correlation is often modeled using such a first-order autoregressive model. And here we have epsilon t is equal to phi times epsilon t minus 1 plus u of t, where u of t is just simply normal with 0 and mean 0 and variance sigma squared. So here the error term epsilon t depends on the previous error term epsilon t minus 1 and a new disturbance term, which is given by this u of t. So this kind of looks like a regression model, and that's kind of where it comes from, autoregressive. It's self-regressing. So basically both, it's regressing on its lagged value here. So basically, if we look at the autocorrelation function for an AR1 process, we see that the autocorrelation between adjacent time points depends on how close different time points are to one another. So basically, the autocorrelation is equal to 1 if the lag is 0. So it's, of course, perfectly correlated with itself. However, if we have a lag of one time point, the autocorrelation is now equal to phi, which is a constant of the model. And then it decays according to phi to the power of h. So what we see here is phi is equal to 0.7. We'll see that adjacent time points, directly adjacent time points, will have an autocorrelation of 0.7. If the time points are removed, are 2 points away from each other, the autocorrelation will be 0.7 squared, so 0.49, and the autocorrelation decays as we move further and further away from each other. So again, the format of V, which we include and which is important in the estimation of the GLM model, it will depend on the noise model that we use. So in the IID case, V is just equal to identity and everything is nice and simple. However, in the AR1 case, we have to incorporate this autocorrelation between, depending on how close time points are to each other. So here V will look like the following case. So it will look a little bit more complicated. And it will also be a bit more complicated to estimate because now we also have to estimate phi, which is this autocorrelation component. So how does this fit into the GLM estimation that we talked about in the last module? Well, again, so this is the GLM model and this is the estimate. So basically we need to incorporate V, this autocorrelation, this variance covariance matrix of this format into the estimate here. And then using that, we can get the residuals and use the residuals to estimate things about the variance covariance matrix. So this is a tricky thing. So this is what we would do if we knew the form, if we knew what V was exactly, if we knew what all the components of V were, we could just estimate beta as in the previous slide. But in general, the form of the variance covariance matrix is unknown, which means that it has to be estimated. This creates sort of a chicken and egg problem because estimating V depends on the betas and estimating the betas depends on V. So in order to kind of solve this chicken and egg problem, we need an iterative procedure. So we begin by assuming a value of V, estimating beta, and then updating our estimate of V, and then iterating between the two. So we need, therefore, methods for estimating the variance components, and there are many such methods that we can use in practice. These include methods of moments, maximum likelihood methods, and restricted maximum likelihood methods. So here's how one such iterative procedure might work. So we begin by assuming that V, the variance covariance matrix, is just equal to identity. So we assume that the data are uncorrelated with each other. And we just simply calculate the ordinary least square solution. Doing that, we can now estimate the parameters of V using the residuals that we got from the OLS. And then we can re-estimate the beta value using the estimated covariance matrix V hat, which we obtained in step 2. Finally, we would iterate this procedure, estimating V hat and beta hat and alternating between the two until we find some sort of convergence. So that's sort of a standard way of doing this type of thing. So incorporating the autocorrelation makes things a little bit more complicated when we assume that the data was IID, like we did in the previous module. So how do we estimate in an AR model? Well, in the AR model, there's a very simple method of moment style estimator, which are called the Yulewalker estimates. So basically, if we have this AR1 model, there's a simple closed form solution for estimating phi and sigma squared, and they're given by the following, which is based on the autocovariance function. So we just simply have to calculate the autocovariance function at lag 0 and 1 and plug this in order to estimate the components of the AR model. So this is a sort of a simple way to do it, and it's fast and it's very useful in fMRI data analysis. The maximum likelihood type methods are a little bit more computationally cumbersome, and they are obtained by maximizes the log likelihood, and this is the example of the log likelihood, and so we just simply have to estimate the parameters associated with V by maximizing this function, and there's many different types of maximization methods you can use to estimate this. Restricted maximum likelihood is very similar to maximum likelihood. It's just that we simply have an additional REML term, a restricted maximum likelihood variance term. So basically, it's the same sort of procedure. We need to maximize this. We need to find the value of V that make this term as big as possible. So what's the difference between maximum likelihood and restricted maximum likelihood? Well, maximum likelihood maximizes the likelihood of the data Y, and is typically used to estimate mean parameters such as beta. However, it can produce biased estimates of the variance. So in the ANOVA setting, the estimate would be 1 over n times the sum of squared differences between the mean. Restricted maximum likelihood, on the other hand, maximizes the likelihood of the residuals. So this can be used to provide estimate variance parameters, and they're very useful because they provide unbiased estimate of the variance parameters. So if you see, for example, in the ANOVA case, what we would have is instead of dividing by n, we would divide by 1 over n minus 1, and this provides an unbiased estimate of the variance components. So that's one of the benefits of restricted maximum likelihood. So many people tend to like to use restricted maximum likelihood because they tend to give unbiased estimates of the variance components. So further, if we were to fit such an AR model across the whole brain, and in this case I'm fitting an AR2 model here, so I have two phis. Phi 1 is for the point that's 1 lag removed, and phi 2 is for 2 lags removed. So, but otherwise it's similar to the AR1 model that we talked about. But the reason I'm showing this slide is I'm showing that the parameters of the model, phi 1 and phi 2 and sigma, actually vary across the brain. So this implies that the same autocorrelation model is not going to hold true across the entire brain. So so for example, you'll see that the autocorrelation seems to vary depending on, say, tissue type and where in the brain you're located. So that therefore we have to kind of fit a separate autocorrelation function for every voxel of the brain, and this can become quite computationally cumbersome in the long run, and it also complicates analysis somewhat. Okay, so this is the end of this module. We've talked about different noise models and how they can be incorporated into our GLM estimate. Okay, in the next module, we'll talk a little bit about performing inference with the GLM model. I'll see you then.